So the problem I'm going to show you is from this textbook, page 280, chapter 8, number 81. A uniform solid cylinder of mass m and radius r rotates on a frictionless horizontal axle. Two objects with equal masses m hang from light cords wrapped around the cylinder. I'm not going to show you guys the questions yet because I really want to create a free body diagram and understand the situation first. It makes physics easier, and I suggest that you make a habit of it. In the book, we get a picture of a cylinder of radius r. It has two strings attached with balls of equal mass at the end of each string. The picture also indicated that angular acceleration is clockwise, so torque is negative. Torque is pretty much just a twisting force that causes objects to rotate. There are two forces, tension acting upward and mass times gravity acting downward. Normal force and gravity have zero moment arm. Moment arm is the length between axis and the force, so they don't contribute any torque. So the equations we're going to be using today are, of course, sum of the forces equals mass times acceleration. And then we're going to use moment of inertia times angular acceleration equals the sum of tension, and acceleration equals radius times angular acceleration. So here is our problem. We have to find the tension in each cord. We know that the sum of the forces equal mass times acceleration. Here is the picture again. Notice the two forces, tension acting up, which means it's positive, and mass times gravity acting down, so it's negative. So that will be the sum of the forces. Positive tension minus mass times gravity equals mass times acceleration. Tension minus mass times gravity equals mass times acceleration. Now we can apply torque, which we know is moment of inertia times angular acceleration. For a solid cylinder, moment of inertia is half the mass of the cylinder times its radius squared. But torque is negative because it's going clockwise, remember? So we'll write torque is negative and substitute the value for moment of inertia. Here, we'll rewrite it as negative torque equals half mass of the cylinder times radius squared times angular acceleration. And we also know that angular acceleration equals acceleration over radius, and we could substitute that into the equation too. Now we can rewrite it as negative torque equals half times mass of the cylinder times radius squared times acceleration over radius. Now, the other thing that we also know is that torque equals tension times radius, and then we could plug that in. And then we'll rewrite it as negative tension times radius equals half the mass of the cylinder times radius squared times angular acceleration. Now we simplify by dividing radius on both sides to cancel it out. We also had to take into account that there were two strings and two masses, so there is two torque. Sorry, I should have done that earlier, but it's alright. We still set tension as mass of the cylinder times acceleration over 4. I also made a mistake in this. I was supposed to take the absolute value of that because tension is a force, and the minus there just means that the direction of the tension is down. But we will still continue and substitute our earlier value of acceleration into tension. I made a mistake earlier, but now I'm going to correct it. I didn't make a mistake on the video, so this is the newer version, and it's going to be me blabbering and doing it on the spot. Yay, fun! So, earlier on we had tension minus mass times gravity equals mass times acceleration. Remember that? Remember how I told you to follow along? Yeah, this should be in your notes. If you're taking notes, you should follow along. So, we're going to look for acceleration. I said earlier that we're going to substitute our earlier equation for acceleration. So we're gonna do that now. Here's our acceleration, and we divide out mass, and then we can rewrite this as tension over mass. Oh, but then what am I doing? This is our acceleration. Cool. Part B of this problem was to find acceleration of each object after the objects have descended a distance of h. And we could use the equations that we found for part A. So the first thing we have, acceleration is constant. And we had acceleration equals tension minus mass of the ball times gravity over mass. And then we also had tension equals mass of the cylinder times mass of the ball times gravity over, was it? 4 mass of the ball plus mass of the cylinder. Then what we do, we'll use this. Oh, what am I talking about? Okay. We take tension and we put it into here, and we can rewrite it as acceleration equals this minus mass times gravity over m. Now there is mass of the ball on both sides, here and here. And then we could rewrite it again, but as mass of the cylinder times gravity over this minus gravity times mass all over mass. Then we can cancel this out. And here, I'll rewrite it because I'm running out of space. And then we end up with acceleration equals mass of the cylinder times gravity over 4 mass of the balls plus mass of the cylinder minus gravity. And we also have gravity here, so we could wait, let me think.